Alrighty, here is a topic that we are past overdue studying. It's called the empirical formula. For quite some time now, we've looked at molecular formulas and formula units of salts, but sometimes in the lab there's only a method for determining the simplest whole number ratio of elements in a compound. For example, there's 28 days in a lunar cycle. The moon goes through a phase of 28 days, every 28 days, from full moon to full moon. And the full lunar year is 364 days. So how many lunar cycles are in one lunar year? Is that obvious? I don't know, maybe. All you have to do is divide the total number of days by the days for one cycle, and you find there are 13 cycles. In other words, the moon goes through its cycles, and there are 13 full moons every calendar year. Sometimes there are even 2 full moons in a month. That's why it's hence the term once in a blue moon. Seriously, look it up. Anyway, similarly, the empirical formula is the simplest whole number ratio of elements in a compound. And sometimes in the lab, that's all you can find. Carbon's usually listed first, then hydrogen, nitrogen, oxygen, and any other elements in the compound. The molecular formula is indeed the formula of the molecule. So if I were to write CH2O, that could be formaldehyde as a molecule, or it could be the empirical formula for acetic acid, ribose, or glucose, although I'm not sure what the bonding here is. Yeah, just by saying C6H12O6, it could be glucose or it could be anything. But the empirical formula for these three is CH2O, because I can divide by 5 all the cross, divide by 2 straight across, divide by 6 straight across. Similarly, I could have a hexane, C6H12, or C6H14, or I could divide both of those by 2 and get the empirical formula like this. So C6H7 is the proportions, but not as descriptive as the full molecular formula. But maybe it's all we can determine in the lab. There could be various other compounds with the formula C3H7, but all I'm saying is that's the simplest whole number ratio of carbons to hydrogens in hexane. Let's try one. This is a hint. The picture shows the structure, if you're familiar with organic chemistry. Benzopyrene, a molar mass of 252 grams per mole, and an empirical formula determined in the lab, likely, of C5H3. What's the molecular formula? Well, what does C5H3 weigh? What's the molar mass of 5 carbons and 3 hydrogens? Add it up. Look at the periodic table for the grams per mole, and it's 63.08-ish. So question is, how many 63s fit into the entire molar mass of 252? The answer is about 4. So instead of C5H3, it's probably 4 times that and 4 times that. So if I went around and counted up the carbons and hydrogens in carbon, 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 took into account the bonding and the hydrogens, it would be C20H12. Interesting. Let's try that again. Another way we can do it is by percent composition. 60% carbon, 4.48% hydrogen. I could then subtract those two from 100% to get the oxygen, but they told me 35.53. The first step in this trickery is to change the change the percent into grams, imagining we have a 100 gram sample. Even though indeed we may not have a 100 gram sample, everything else will be proportional. So 60%, 60 grams, 4.48%, 4.48 grams, 35.53%, 35.53 grams, 16 grams per mole for oxygen, 1 gram per mole for hydrogen, 12 grams per mole for carbon, changes the grams to moles. Then, the next trick in this step is to take each of those mole amounts, 4.99, 4.45, 4.45, 2.221, and compare them to the smallest number, assuming this smallest number implies a 1 of those atoms in the empirical formula. Well, it works pretty well for this one, it works pretty well for this one, but 2.249 is not very close to an integer. This is very close to an integer. I wrote C2.25H2O1. I'm happy about this, but I'm not so happy about that. So the truth is I must probably take each of these 1 and 2 and 2 1/4 times an integer in order to make whole numbers of atoms in the empirical formula. I determined that I probably should take everything times 4. Take it times 4, take it times 4, take it times 4, thinking about 2 1/4 as 9/4. Take this times 4 and you get 9. Take this times 4 and you get 8. Take this times 4 and you get 4. Usually it's not that complicated. Sometimes this division by the smallest number of moles will create integer numbers, and that tells me straight away what my empirical formula is. Alright, let's try that again. Let's see. Compound is determined to contain 72.4% iron and the rest is oxygen. Subtract 72.4% from 100 to get the percent of oxygen. You know the tricks. Imagine the percents as grams. Oh, that's kind of poor form. I wrote percent and changed the percent to moles right away. That's lazy. I should have written grams here and grams here. But that was the percent, and write the percent as grams, so 72.4 grams to moles, and 27.6 grams of oxygen to moles gives me a 1.3 moles and 1.73 moles. Divide each of those by the smallest number. Of course, that gives you 1.33 here. Dang, rats, shucks. I suppose this is going to have to be multiplied by an integer as well. So another name for 1 1/3 is 4/3. So what number should I multiply straight across here and here to change into integers? How about a 4 and a 3? That's the empirical formula. Probably the formula unit for the salt as well, the formula for the salt. But find the molecular formula. There's another one. If you feel really brave, you could pause it right now and go for it. Change percent to grams, change grams to moles, compare each mole amount to the smallest mole amount. That gives you the empirical formula, we hope. And the overall molar mass is 580. Jeopardy music. Pausing the video or not. And here's the answer. Change percents to grams, change grams to moles. By this time in your chemistry career, you're probably good at changing grams to moles. Compare each mole amount to the smallest number of moles. And this one's very close to 1, that's very close to 2. So the empirical formula P1N1Cl2, and that adds up to 1 phosphorus, 1 nitrogen, 2 chlorines, adds up to 115.88. Question, lastly, how many of those 115.88s are in 580? And the answer is it's very close to 5. So if there's 5 of those empirical units in the molecule, take this times 5, take this times 5, take this times 5, and that's your molecular formula. Ta-da! Thanks guys, see you soon.